Okay, here we go. Now, I forgot to mention, always do your chapter review. It goes over the important stuff, and it's very important for you to, and notice it's broken down by section, and it's very helpful for you to go, oh, I didn't quite absorb that. And then they'll even have a self-chapter self-test. Now, I don't do these in this review. I only do the homework because the homework, these tests are simply a review of the homework. The other one I missed in 2.5 were these last two questions, which I might as well do it. So if we're to, it's the answers for this chapter coming up, but if we were to look at this, explain how to determine the value of x that gives a maximum for a transform sine function in the form of this. So you will always find your maximum based on these two things: how much it's been transformed to the right or left, and how much the period has changed. So right now they remind you that the current maximum is at 90 degrees and 1, which is true. Okay, so how do you find the new max? Well, the point is the max will be found a quarter of the way through the period and then adjusted whatever the d adjustment is. So in that case, to find the new period, you simply divide by k or multiply by 1 over k. So step 1, take 360, multiply by 1 over k, which is the same as dividing by k. And if you're working in radians, it's 2 pi instead of 360. After you do that, take the new period, and if it's a minus sign in front of d, add, oh, actually, now that you found the new period, find out a quarter of the way to the beginning of this period. So let's say you find out the new period is 10 seconds. So the beginning is 0 seconds normally. So find out the quarter distance between 0 and 10. The quarter distance is 2.5. So normally the max would be at 2.5. Now you take that 2.5 and you adjust right by the d amount if it is minus d, and you adjust left by the d amount if it is plus d. That's because you go the opposite direction. You can also find, once you find the new period and instead of finding the quarter spot, find the new start. Find the new start point by doing the same steps I just described. And then once you find it, find a quarter of the period and add it to the new start point. And that also works. So either way, the maximum of any sine curve when it's in its parent is a quarter of the way through the period. So that's how you do that one. Then this question is deceiving, and number 14. And it's because it's measuring the speed based on the change of time. So be very careful. So read the question. The question says, if the speedometer of a car shows the vehicle's instantaneous velocity, which is true, it shows the vehicle's velocity at any one moment, or a rate of change in position, every 5 seconds, Myra records the speedometer reading in a vehicle driven by a friend. She then plots these values. When Myra begins considering rates of change shown on her graph, what quantity is she looking at? Explain what different scenarios in Myra's graphs mean. Okay, so it helps if you put in some different values. So let's say at 0, she's going 50. And then Myra waits 5 seconds, and she's going 55. And this is kilometers per hour, or whatever units your speed is. It's very important to keep that in perspective, and also keep in mind this is seconds. And then she checks 10 seconds later, 5 seconds later, and she discovers he's really accelerated a lot. And then 15 seconds, let's say, kept the same speed. And then 20 seconds really gunned it. And then 25 seconds suddenly hit the brakes, which is crazy. So that's like a collision, or had to jam on the brakes. Goes from 100 to 0 in 5 seconds. Probably not even possible. And then if you were to plot this, you'd say, well, when she first checked, they were going 50. And then when she checked 5 seconds later, she's going 55. And then suddenly it jumps up quite a bit to 70. And then it stays flat at 70. And that goes quite a bit up. And I should actually bring this down a bit to get that last 100 squeezed in there. Then it goes quite a bit up in the next second to 100. And then suddenly she sees a traffic accident. And they jam on the brakes. And they start to there. So then we're going to draw a line and we see, well, that's fairly consistent. That's quite a bit more acceleration. Then there's no change in speed in that one, even though the line's not correctly drawn. Then there's a huge acceleration here, obviously, not quite drawn well. And then look at this one. You can see what's going on. Now, what do those slopes mean? Well, keep in mind that the y-axis is in kilometers per hour, and that's a speed, not a distance. And that the x-axis is in seconds. So if I were to take the slope of any of these things, I would be taking delta y, which would be in kilometers per hour, and dividing it by seconds, and I'd get a very unusual reading, and it would actually help if I'd recorded her speed in meters per second or something in seconds. But anyway, I get a very unusual reading. That's kilometers per hour dot second, which means every second that passes, her speed is changing or is altered. And it's hard to think of it when it's in kilometers, hours, seconds, because it doesn't really exist. And you'll probably be more familiar with in meters per second squared. And meters per second squared is known as acceleration. So what that slope is showing is how fast she's pressing the gas. So here she's pressing the gas a little, and when we take that difference, we discover 5 kilometers per hour over 5 seconds, and that's just simply 1 kilometer per hour per second. So she's accelerating 1 every second. Her car is increasing speed by 1 kilometer, which makes sense. This one we discover she's going up 15 kilometers in 5 seconds, so her acceleration is 3 kilometers per hour per second. And this one, it's the same speed, and we discover a slope of 0. This one we discover she goes from 70 to 100 in 5 seconds, so it's 30 over 5, and it ends up being 6 kilometers per hour per second. And this one's 100 seconds divided by, in 5 seconds, 100 kilometers an hour to 0, so it's a negative slope. And 100 divided by 5 is negative 20 kilometers per hour per second. All of these are showing the acceleration of the car, so the slope is actually measuring acceleration. The y-axis is measuring speed, and the x-axis is measuring time, and the slope, kilometers per hour per second, is known as acceleration. So it's showing just how much gas is being pressed, and every time the slope is going up, the gas is being pressed, and every time the slope is declining, the brake is being pressed, because you're reducing your speed down to a new speed, which is what happens when you press the brake. But you can see, right away, you can see something happen here, who goes from 100 to 0 in 5 seconds. So it's always good to have an example. Explain what different scenarios on Myers' graph mean, such as when the graph is increasing, but the rate of change between the points on our graph is decreasing. So it just essentially means that if the speed is going up or changing, it's an acceleration. If the speed is going down, it's a deceleration. And if the speed stays consistent, nothing's changing. She's just maintaining her speed. And it's good for physics class. Okay, so let's look at this one. Estimate the instantaneous range for a graph of f of x is equal to x squared. So let's look at that graph. And they want us to take it -2. And at -2, the reading will be 4. At -1, the reading will be 1. At 0, it's 0. At 2, it's interesting they took 2. At 2 again over here, it's 4. They should have taken 1, 1. And then at 3, it's 9. All right. So if you were to draw tangent lines at any one of these points, you would notice, oh, well, the 2, 1, -1 going down is almost the same as the 2, 1 over here, but it's going up. And you'd notice the 1, 1 tangent lines like that. And you'd notice the 0, 0 tangent lines like that. And you'd notice the 3, 9 tangent lines, the steepest. And I'm going to let you in a little secret. You would do the whole f of x. So you do f of -2 minus f of minus 2 plus h all over your h over and over again. And what you're going to discover is for this one, you're going to come up with minus 4 as your instantaneous rate of change. So for minus 2 comma 4, you're going to discover the instantaneous rate of change is that. For minus 1 comma 1, you're going to discover your instant rate of change is minus 2. For 0 comma 0, you're going to discover your instantaneous rate of change is 0. And for 2 comma 1, you're going to discover your instantaneous rate of change is 2. And 3 comma 9, you're going to discover your instantaneous rate of change is 6. Now, I'm going to give you a little hint. Let's look at the x values here instead. So in green, I'm going to do the x values only. And keep in mind the instantaneous rate of change. Do you notice a pattern? Do you notice a pattern? Oh, that stayed red, but that's okay. And they try to throw you off by doing different values. And so this one is, sorry, this is the x rating, and this is the thing. Now, do you notice a connection? What's the relationship between an x value of minus 2 and minus 4? How do you turn minus 2 into minus 4? Huh. Well, you multiply by 2. Let's see if that stays the same. How do you turn minus 1 into minus 2? Oh, you multiply it by 2. So that was multiplied by 2. 0 to 0, multiplied by 2 still works. Plus 2, oh, sorry, the rate of change here is plus 4. Plus 2 to plus 4, multiplied by 2. Plus 3 to plus 6, multiplied by 2. Now, if you do it for x cubed, you're going to discover that the multiplier is 3. Now, notice the multiplier was 2 when it's x squared, and later on when it's x cubed, the multiplier is 3. So one might believe, actually, it's going to be even weirder than that. It's going to be 3. It's going to be 3 times the x squared, and this one's going to be 3 times the x. And you can say, 3 times the x, 3 times the, or 2 times the x down here, rather, and 3 times the x squared up here. And you're going to discover that when you take the exponent down here and lower it by 1 rather, you're going to get a formula that will give you the instantaneous rate of change. So to say that again, if I have x squared, you're going to discover in time that the formula for the rate of change is 2 times the x value. If I have x to the power of 3, you're going to discover that the rate of change formula is 3 times x squared. If I have x to the 4, you're going to discover the rate of change formula is 4x cubed. So each time I'm lowering the power by 1 and putting that original power in front of the x multiplier. You're also going to discover it works for a line as well. So to get rid of all these, you're going to discover the rate of change for a line that's 2x is simply 2, which makes sense. It's simply 2 is the slope. You might say, well, what happened to the x? Well, x here has power to 1, and when it becomes power 0, it becomes 1, and 2 times 1 is 2. That's what happened. But you're also going to discover some interesting things, that if you had 2x squared here plus 3x, that you can actually come up with the formula, which is 4x plus 3. This is the formula for the rate of change for this graph. And that's what calculus will all discuss, is all sorts of formulas for rate of change for basic parent functions. Now, that's important that I didn't quite cover it, so I wanted to do it. We're on to 3.2. We did 3.1 here before. So, characteristics of a polynomial. So what they want you to notice is, how can you predict some of the characteristics? So we went into a lot of that last time, of how ones that have even exponents all start in quadrant 2 and end in quadrant 1. Quadrant 2 and quadrant 1. Down here, because it starts in quadrant 3 and ends in quadrant 4, I can tell you it's an even exponent with a minus in front of it. And then here I can see how many turning points. 1, 2, 3, 4, 5. So it's probably x to the 6, and because it starts in quadrant 2 and ends in quadrant 1, it's probably a positive x to the 6. And sure enough, it's positive 2x to the 6. This one I can tell is an odd function because it starts in diagonally opposite quadrants. So it starts in quadrant 3, ends in quadrant 1, and has 2 turning points, goes through the x-axis 3 times. So I can tell you that's a positive coefficient with an x to the power of 3, and sure enough, positive 1x to the 3. This one also starts in a quadrant diagonally opposite, so it's an odd function. I count the turning points. I get one turning point here, one turning point here, turning point, 4 turning points. So it's probably x to the 5. It also helps that when I count the x-intercepts, there's 5 of them. It's because it starts down below and ends up top. I can tell you it's a positive coefficient in front of it. Sure enough, it's positive 2x to the 5. It's these kind of patterns they want you to notice. But also notice that counting the turning points isn't always useful. So this one is a power to 5, but you wouldn't know it from counting the turning points. You would notice when you start noticing weird flat end bends, you could count the x exponents and determine it. But it won't always help to figure it out. But it helps you to notice that, oh, sometimes x to the 5 will still look like something else. This one's an x to the 3, but it starts way up here in quadrant 2 and ends up in quadrant 4. Anytime the start and ends are diagonally opposite, it's going to be an odd function. And every time they're mirrored, starting and end in the y-axis, it's going to be an even function. But because this one starts up here and goes down, I can tell you it has a minus coefficient. It kind of bends once, so I'll say it's a minus x to the 3, and sure enough it is. Notice it only crosses the x-axis once. This one only crossed the x-axis once, but I can kind of see it was starting to change direction here and then changed its mind. So I'll count that as a bend of 2. And then there's a bend of 1 there. So I'll say this is an x to the 4 because it starts normally and ends normally. I'll say it's a positive x to the 4. Now I was able to determine that because whenever you have a bounce back or a double wiggle, you can count them as 2. So I can count it as 2 here, 1 in the middle, and one there. It kind of gets tricky after a while. Here they say copy the following tables and complete it. So it's a degree 2. What does that mean? It means the largest power in here has a power of 2. Even or odd? Well, because 2 is an even number, it's even. Leading coefficient, what's the number in front of this 2 degree? It's 1. End behavior, as x goes to negative infinity, so as we look way on the left of the graph, y goes to positive infinity. As x goes to positive infinity, y goes to positive infinity. So both times y goes to positive infinity when the leading coefficient is positive and it's an even function. How many turning points? Just 1. And then it asks you to do the same thing with these. It asks you to study them. And then it also asks you to realize what is the old definition of an even function. An even function is one that mirrors in the y-axis. When you switch the x to a minus, if you come up with the same equation, it's an even function. When you switch the x to the minus and you come up with the same equation but has a minus in front of it now, it's an odd function. And it's neither odd nor even when you switch the x to a minus 1, you get a totally different equation. Or visually you can see it doesn't reflect through anything. The reflection in the odd function is through the origin. So the origin acts as a mirror. Then they go about and help you recognizing absolute minimums and absolute maximums. And that's absolute minimums are the absolute lowest point. And local minimums are a min point, but that's not the lowest point. So they say, you know, what's the difference between absolute minimum and absolute maximum? And then they want you to describe the end behavior. So it's an x to the 5. So normally it would start in quadrant 3 and end in quadrant 1, except it's a minus. So I'm going to reverse that and start it in quadrant 2 and end in quadrant 4, the opposite quadrant in diagonally. And I'm also going to say it can have up to 5 x-intercepts and 4 turning points. This one is an even function, and it has a positive coefficient, so it's going to start in quadrant 1 and end in quadrant 2. It can have up to 4 x-intercepts and 3 turning points. And it goes through that, and we kind of discussed it last time. And then reasoning with the characteristics, you know, what can you determine for sure? If you know it, x from minus infinity goes down to negative infinity, and x positive infinity goes down to negative infinity, I can reason that that's an even degree polynomial that has a negative in front of it. And it can have at least 2 zeros because it's got to cross the x-axis twice. And then it just goes on about how many different possibilities. And here are some possible graphs of the function. And then it just reviews what you should know. End behavior is simply as I follow the x all the way up to positive infinity, where does it end? And beginning behavior is as I go way on the left of the graph of negative x, negative infinity, where's the y values? So those are called end behaviors, or where it ends, and beginning, I think they're called beginning behaviors. Turning points, and they give you a formula, degree minus 1. Number of zeros, it can have up to these. The symmetry is something you got to memorize. And then it just runs you through check your understanding. All right, I'll try to make sure I'm more thorough. Okay, state the degree, leading coefficient, and end behavior. So A, degree, 4. Leading coefficient, negative 4. So I'll just do negative 4. And end behavior, so where does it end? So it's negative, so it ends in quadrant 4, which means as x goes to, where's the goes to? Infinity, positive, y goes to negative infinity. Okay, next, B. Degree, 5. Leading coefficient, positive 2. End behavior. Well, I'll just go with the whole thing. It begins in quadrant 3, ends in quadrant 1. So as x goes to infinity, so does y. The next one. Got to put it in the right order. When you see the largest degree, you discover that the largest degree is 3. Leading coefficient is minus 3. So this is an opposite of a normal one, so it's going to begin in quadrant 2 and end in quadrant 4. And that means as x goes to infinity, y goes to negative infinity. That's what quadrant 4 is. Next one, you have to multiply out all these x's, and that's all you have to do. So you get 1, 2, count the x's, 4 x's. So if I multiply them, I'm going to get x to the power of 4. So that's the degree. The tough part is figuring out the leading coefficient. So then you just look at the number in front of it. It says x's. 2 times 1 times 3. That's going to be 6 times 4, 24. So the leading coefficient is positive 24. Then you're going to say, okay, where does that begin? It begins in quadrant 2, ends in quadrant 1. So as x goes to infinity, positive infinity, so does y. And there you go. The more you learn this, the faster it gets, the easier you'll do in a test. Determine the minimum and maximum number of turning points for each functions in question 1. Okay, min and max. Okay, so I'll do it all over again. A, and it's going to say determine the min-max number of zeros. So I'm going to do it both. So for A, because it's degree 4, you can have 4 x-intercepts, or 4 zeros, and you can have 3 turning points. And the next one, because it's degree 5, you can have 5 x-intercepts, also known as, or 5 zeros, and you can have 4 turning points, which means you can have 4 min and max. C, because it's degree of 3, you can have 3 x-intercepts, also known as zeros, and 2 turning points. And D, because it's degree 4, I think we said 1, 2, 3, 4, you can have 4 x-intercepts, or 4 zeros, and 3 turning points. And then for each of the following graphs, decide if the function is even or odd and the leading coefficient positive or negative. Okay, that should be easy enough. Just look where they start and where they end. So, because this one starts on the quadrant and ends on the quadrant beside it, it's even. And because it's in an unusual start, it's negative. No, I'm good, I'm busy. And then this one, number 2, also because it starts and ends in quadrants side by side, it's even. And because it's facing downwards, it's negative. the leading coefficient's negative. This one, it starts and ends in diagonally opposite areas, so it's even. And because it's opposite, normally it would start at the bottom in quadrant 3. It's a negative leading coefficient. This one's your standard parabola facing up, so we know its degree is 2. So that's even. And it's positive because it's facing up. We already know that. So positive. And then finally this one, it starts in diagonally opposite and ends in diagonally opposite, so it's even. And it ends in opposite areas that it would normally, so it's negative. And then this one is finally a normal one. That's a normal odd. Oh, sorry. This one up here is odd, not even. They're diagonally opposite. This one's diagonally opposite as well. It's odd, but it's normal. So it's got a positive leading coefficient. Not too hard. You can do them pretty fast once you get knowledgeable. And then it's doing number 4. Okay. And you can see, describe the end behavior of each polynomial function using the degree and leading coefficient. So I'm going to do it over and over again. A, the degree is 2, so it's even. The leading coefficient is positive 2. So starts in quadrant 2, ends in quadrant 1, which means end behavior as x goes to positive infinity, y goes to positive to the same. In B, because it's degree 3 and a negative 1 leading, it is going to start in quadrant 2 and end in quadrant 4, which means as x goes to positive infinity, y goes to negative infinity. In C, because it's an odd and leads with 5, it is odd, so it starts normally in quadrant 3 and ends in quadrant 1. And so that means as x goes to infinity, so does y. Essentially, if you end in quadrant 1, your y goes to infinity. If you end in quadrant 4, your y is going to negative infinity. So D, we have a leading coefficient of -2. The highest power is 4. So that means we have an even function. Opposite, it's going to be, instead of starting normally, it's going to start in quadrant 3 and in quadrant 4. So as x goes to infinity, y goes to negative infinity. And E, it is still an even function with a positive leading coefficient. So that means it's going to start in quadrant 2 and in quadrant 1, which means as x goes to infinity, y goes to infinity. And then the final one has a 5 degree and leading is negative. So that means it's going to start in the opposite. They're going to flip through the x-axis. So we're going to start in quadrant 2 and in quadrant 4, which means as x goes to infinity, y goes to negative infinity. Okay, we're going to match each graph. So this is a degree 3. So we know it can't be that, it can't be that, and it can't be that. And it could be any of the bottom ones. Now, notice that it can't be this one because there's too many turning points. And that means it could be here or here. And because it's got a positive, we'll have to look at other ones before we determine if it's B or D. Okay, now we could figure out the the y-intercept is 2, and it doesn't look like it's 2 there. It looks like it's more likely this one. That could be 2, but I don't think so. I'm going to have to go with D for now. So let's just call it D. Now let's look at this one. This was an even function and it's negative. So it could be this one. It can't be that 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 one. So since we've ruled out everything, this is the only one that starts in this quadrant, ends in this quadrant, and it also looks like it has 3 turning points. So that one is definitely A. And this one for now we're saying is D. And then this one, it's a parabola and it's facing up. So obviously we can rule out everything except that one. So that one must be E. So you can see once you get good at this, it's quite easy to rule it out. That says A and that says D, I think. And then this was an x to the power 4 and it's facing up. So it can't be that, can't be that, can't be that, can't be that, can't be that. So it must be C. So this one's a power to the 5 and it's negative. So it can't be this one, can't be this one, can't be this one, can't be this one, can't be this one. This is the only one that has 5 turning points. So it's definitely E. So this last one's going to tell us what we need to know. And I can sort of see right there. That's what I need to know. So I can tell you right away that that's going to have an X-intercept. And that one looks lower. So that last F1 is definitely B. Sorry, a Y-intercept, not an X-intercept. And there you go. Now, I could also figure out some more points on this. For instance, I can definitely see if the point minus 2.2 is a possible intercept point, and same with over here. We could figure out more things, but the Y-intercept is a pretty good indicator. So there you go. Give an example of polynomial function that has, I hate these questions. I think they're kind of useless, but I understand. They're just trying to get you to think in terms of words. And you know, sometimes you might think these things are useless. What they're really trying to get you to do, why calculus is part of science when it's not used for science and functions, is to weed out the people who don't have the patience to do this analysis. And don't worry, in high school, a lot of people don't want to do it, so you don't have to. And you can always take it up later in life. You're just going to have to take some courses over again, which isn't a big deal. So give an example. So in A, something that ends in as x goes down to negative infinity, and y is in negative infinity, but on the other side, as x goes to positive, y goes to positive. That can be any odd polynomial with a positive leading coefficient. So example, positive 3x to the power of 3. Another example, positive 7x to the power of 9. Doesn't really matter so long as it meets those conditions. In B, as x goes either way to infinity, y is going up. So that means we have y is going to be an even polynomial with a positive leading coefficient. So that an example would be, 4x to the power of 4. C, because as y goes to each infinity, y goes downwards, we're talking about an even. Y is equal an even polynomial with a negative leading a coefficient. You can always punch these into Desmos and see. So you're talking with y is equal to minus 6 x to the power of 8. It doesn't matter what the leading coefficient is. And in D, as x goes to negative, y goes to positive. As x goes to positive, y goes to negative. So they're opposite ends. So it's an odd polynomial with a negative coefficient leading coefficient because it's starting up in quadrant 2, which would be something like y is equal to negative 7x to the power of 3, or x to the power of 5, or even negative 7x, a line. Sketch the graph of the polynomial satisfies all these sets. Oh, geez. Okay. I mean, I'm going to loosely sketch. 3 zeros, 3 turning points, degree 4, positive leading coefficient. So all positive leading coefficients of degree 4 will end up here and up here. W's are the classic thing. Since it has 3 zeros and 3 turning points, this one has 3 turning points, but notice it has 4 zeros. So that means I have to draw it like this. Let's go through there. Let's come up and just touch once here, come down and go down. There, I have 3 turning points, and I have 3 zeros, and I start in quadrant 1 and end in quadrant 2, and I have a degree 4. And there's a good example. Degree 4 this time with a negative leading coefficient, only 2 zeros and 1 turning point. Ooh. So 2 zeros and 1 turning point. It's going to be something like that. And then it's going to be sort of flat here. And you're going to see that with something like y is equal to x to the negative x to the 4 plus 6. Okay, so I'll just show you that, actually. There you go. There's a good example. One turning point, 2 zeros, and a degree of 4. And the negative makes it start and end down here. Good example. Okay. And what's the next one? Degree 4, positive leading coefficient, 1, 0, 3 turning points. Whew. Okay, well that can be a lot of things. So 4 is going to be up here, but we only want 3 turning points. So 1, 2, touch, and come up. So I got 3 turning points, which is normal, 1, 0, and it starts here and ends here, so it's positive degree 4. There you go. So the next one, degree 3, negative leading coefficient, 1, 0, no turning points. Okay, so a negative, that's a positive. So a negative is going to come here, go right through x-axis and go down like that. So a good example of that would be with no turning points, y is equal to negative x cubed. See, that's not really a turning point. It's kind of like a weird, what I call slide. Gets flat for a bit and then continues on its way. Never really turns. Okay, what's the next one? Degree 3, positive leading coefficient, 2 zeros, 2 turning points. Okay, so that's kind of a normal one, like that. So a good one for that one would be y is equal to x plus 2 times y is equal to x times x minus 2. There you go. 3 zeros, 2 turning points, starts in quadrant 3, ends in quadrant 1. And then finally, 4 degree, 2 zeros, 3 turning points, and a limited range. So they're just kind of making you stay below y is equal to 5. It didn't say leading coefficient, so it just means I'm probably going to have it do this. So I have 2 zeros and 3 turning points, so that's normal. I can do this, do that, come up, and then go down. So I only crossed x twice, but I have turning points, and the most it would come up to here, oops, is 5. So a good example of that would be y is equal to negative, I don't know, a couple of x plus 2s plus 1s, and then x, and then it probably has a plus 3 or plus 5 in there. So let's see if we can actually construct that. So I'm going to add one more in here, x minus 4, and I'm going to add, well, I'll just figure out where that one ends. It ends at 9, so I'll just subtract 4. And now I got to make it negative, so it doesn't cross. And now I've got to subtract a bit more, 7 more. So you'll see that the highest point here now is at 5. And yeah, I cheated. I let Desmos do it. I have 4 zeros here, though, so I don't think I quite agreed with the rule. I had to keep this last one up above. So to do that, you make all your intercepts as close as possible. Well, I think I kind of almost did it there. Yeah, and then all I have to do, oh, no, not quite. 2. And then all I have to do is, it's got to be that middle, these middle points have to be a little further out. So this has to be like 2, and this has to be 3. And let's see if I can, yeah, that might do it. So then I just have to be able to raise that by 7 minus 4. There. I still crossed twice. Maybe if I get rid of this entirely. Pretty hard to figure it out just by random chance. That might do it though. There. almost 2.16 or something. Anyway, I think I could do it in factored form, or I think I could do it in by figuring out a vertex point. But at least that's close. It didn't ask me to come up with it anyway. Explain why odd degree polynomial functions have only local maximums and mins, but evens have absolute. Okay, that's because if you look at the beginning, of an odd function, it starts and goes on forever down here, and starts and goes on forever up here, which means the max is infinity. And the max down here is negative infinity. And that means any maximum you find here is not a true max, because these are the true maxes. It only can be local maxes, because the true max is plus infinity and negative infinity. Whereas the even functions, which can look like W's or weird camels, because they start way down here and end way down here, these are definitely the absolute maximums. So you can only have absolute maximums for even functions, even if I draw that the other way. That has absolute minimums. You can even add to that only negative leading coefficients, even functions, can have maximums, and positive leading coefficients for even degree functions can have maximums. Ray noticed that the graph of this, which so we're missing some numbers, right, is symmetrical with respect to the origin, and that it has some turning points. Does the graph have an odd or even number of turning points? So if it's reflective in origin, it means that this side of it is going to be mirrored straight through it. So it has to be odd. And then, does it have an even or odd number of turning points? So because it's odd, it doesn't have to have an even, odd, or no, it can have either. But if you're going to max out the turning points, since it's an odd function, it will have an even number of turning points if you use the maximum turning points. And I should check how they word that in the book here, because I did write down the answer. So that one is question 8. And it's all to the right here. An odd degree polynomial can have only local max and mins. Yeah, that's number 8. An even number of turning points. So they're using the maximum number of turning points. And we're going to just finish off now. Sketch an example of a cubic function with a graph that intersects the x-axis at each number of points below. Only 1 point, 2 points, or 3 points. So we have to have a cubic function. Doesn't matter how you do it. That's quite easy if you know the parent graph cubic function. We'll have 3. And if you want to make it easier on yourself to come up with 2, you're going to leave 1x cubed like that, and then you're just going to add an extra factor, or x squared rather, and that will create 2 turning points. And finally, if you want to use 3, you can just leave the x in there, do an x minus 3, and do an x plus 3. And that will cross the x-axis twice, because I've pretty much told it has 3 factored different 3 different factors, which means it'll have 3 x-intercepts. If I tell it only has 2 different factors, it will only have 2 x-intercepts. And finally, if I tell it only has 1 possible factor, it will only have 1 possible x-intercept. 1 point, 2 point, 3 point. Sketch an example of a quartic function with a graph that intersects the x-axis. No points, 1 point, 2 point, 3 points, and 4. Same thing. So if I want to do a quartic function, I can start with the parent, and that intersects at 1. So there's 1. If I want 0, I just got to raise it above the graph. If I want 2, I just got to lower it below the graph. If I want 3, I've got to get rid of one of these degrees and create a new function like x minus 2. And because I've kept that like that, I should probably actually, that's 2, create a new one like x minus 1. There, I now have 3 x-intercepts. And then finally, if I want 4 intercepts, I just create 4 unique factorables. Because these factors will also always be the x-intercept. So if there's 4 different ones, there's 4 different x-intercepts. That's how you think of it. Okay. The graph of a polynomial function has the following characteristics. Its domain are the set of all real numbers. There are turning points x here, here, and here. So these are the factors. Oh no, those are the turning points. So those will be the peaks. Draw the graph at 2 different polynomial functions that have these characteristics. What additional characteristics would ensure that only one graph could be drawn? Well, the x-intercepts. If you add x-intercepts, it's only one graph. And those are the turning points. Interesting. So the turning points, the derivative will be 0. I would prefer if they told me the x-intercepts. So let's see. So one of them is going to, where's one of the x-intercepts? It's going to be at -2. Where's one of the other x-intercepts? It's going to be at 0. Let's try that. And where's the other turning point? It's going to be at x3. Okay, so that's that. So it's 3 turning points. So that could be almost anything. Okay, 3 turning points. X minus 2, x minus 1, x, and we'll do x plus 1. So that gives me the x-axis there. So the question is 3 turning points, and the turning points are at -2, 0, and 3. I'd have to spend more time studying this to create the max points, because I forget the simple trick. Yeah, I mean, I can get to -2 just by subtracting the whole thing by 1, but that doesn't make one of these maxes at 0. I think I could just do that. And that also doesn't work. I'd have to study that more. Like I said, I don't like the theoretical. The mining town of Brighton was founded in the 1800s. Population-wise, modeled by this. So when it started, you always just look at, and this is in hundreds of people. So if you look at the y-intercept, that's how many people started. So in 1900, you had 700 people, where x is the number of years. What was the population of the town in 1900? Well, I just did that. Based on the equation, describe what happened to the population over time. So we're just going to put this in a formula. Minus 1.1 x to the 4, I think it was, plus 0.5 x to the 3 plus 0.4. So it says x to the 3 again. No, x to the 2 plus 10x plus 7. So let's have a look. Now we're going to also just pay attention to x is bigger or equal to 0. So the town started at 700 people. It grew quite quickly to 6,700 people, 6,707 people. And then it went down to 0 by the year 7.5. So I would suggest a gold rush. Another thing, people moved there and the water got poisoned, or ran out of water, or they were attacked by invading forces who then burned the village down and left. But because it took years, or a plague, so all of a sudden they all got sick and slowly died off or moved. Or radioactivity in the water, or chemicals in the water from the new chemical plant. or drought. All sorts of things can diminish a population. Lack of food, if they're primitive. It's 1900, so they're not that primitive. If a polynomial function is degree n, where n is a positive even integer, decide whether each of the following statements is true or false. F is an even function. No. Even is based on the y-axis, and you can't determine it from this information. F cannot be an odd function. F cannot be an odd function. F will have at least one 0. No, because it's even. It can be right above the x-axis. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to infinity. That is true. If its leading coefficient is positive. That is only true if the leading coefficient is positive. Let's see what the book says. So the book says, and this is 14. Did I forget? Oh, I didn't even get 14. Oh, well. If you needed to predict the graph or equation of a polynomial function, and we're only asked to ask 3 questions about the function, what question would that help you the most? The x-intercepts, the turning points, and the end, beginning and end behaviors. Or, actually, you know what? The degree, the leading coefficient, and the x-intercepts. There you go, even better. Extending, suppose that f of x is equal to this. What must be true about the coefficients if f is an even function? If it's an even function, all the coefficients, I think, should be 1. That would probably be true. It's a good question. I don't know that one. Suppose that it's this. What must be true about g? If it's an odd function. So even would be reflected in the x-axis, which would mean you should really have, well, I mean, b could be 0. You know what's nice about this is you can actually set it ax squared plus bx plus c. And you can just give it all. And it's not an even there. So what happens if this is 0? So when b is 0, we definitely get an e is this. C can be 1, or I believe it can be, actually C can be anything. Doesn't matter, it's going to be even. B should be 0, and I believe A can probably be anything. Yeah, A can be anything. Because you're only expecting a stretch. But it helps if B is 0. Now, if we add the degrees there, we add a slider. So in this case, I believe, so you see that. In this case, I think it believes it helps if C is 0, so that it goes through origin. We'll make these all 1 to see what happens there. That doesn't work. Oh, sorry, we had to add D. D is 0, I'm thinking, and C is 1. And I'll put it in the right order. So yes, that does, I believe, create a origin reflection. C can be anything, it looks like. No. No, it can't. That's not mirrored properly, I don't think. No, it's not. Same with A. So I think C and A might have to match. Yeah, so C and A, if C and A matches, it looks like it might do it. Not quite. Some very complicated question to answer, and I don't think I'm capable of answering it this time. So there you go. It may have helped those. Again, I'm not, what must be true. I think it's best to look in the back for that. I'm not good at the hypotheticals.